Hi, welcome to CEE122 recitation 6, and this recitation will go through the homework solution for homework 6. So let's look at the first problem, 5.39. Gas flowing in and out of the chamber are shown for the condition shown. Which of the following statements are true for the application of the control volume equation to the continuity principle? And we have the chamber look like this. And to answer all these options, we will need to apply the Reynolds transportation theorem and to see the general form of the continuity equation. So just a quick reminder that in the Reynolds transportation system, that we have the system boundary, which is a closed system, and this is at the time t, and at the next time step, it becomes this. So this is the closed system that at the time step t plus delta t. And the Reynolds transportation theorem formalize the description for this closed system. And that's become that this part is our control volume, and the surrounding of this intersection area is the control surface. And this boundary is the system's boundary. Okay, so that we can analog this diagram into the figure. So this middle part is our chamber, and this part is the inflow to this chamber, and this part is the outflow of this chamber. Okay, so these two are actually equivalent to each other. So what we know from this RTT theorem is that the dB, we usually write in larger d dt, which is equal to dB system divided by dt is equal to 0, because this is a closed system. There has no change along with respect to time of this closed system. But if you view at this this middle part, when you derive the equation, which you can see in the textbook, we can separate this into the portion of control volume and plus the control surface. And these parts describe the inflow and outflow relationship, and this describe the change within this control volume. Okay, so what we know here is that the system is not 0, because we do have our closed system in this boundary. Okay, something like that, but I mean, I just analog this diagram into this figure. But yeah, we do have a control system here, I mean the closed system. So A option is not correct. B, we say that this closed system will not change with respect to time, and that is correct, and that is what RTT theorem tells us here. So B is correct. And we have the control surface term showing the option C, which is this term. So we want to know whether the inflow is equal to outflow mass. So let's calculate that. the mass that going out is equal to rho AV at outlet, which is denoted as these two, and this is equal to 2 because the rho 2 is 2. This is 2. This is 2. Okay. Times 0.2 times 5, and this is 2 kg per second. And M in this inflow mass is equal to Hw1 A1 V1, and that is equal to 3 times 0.1 times 10, and this gives us 3 kg per second. So we know that the inflow is not equal to outflow, so this equation is not 0, is actually equal to -1. So this is not correct. And because this term here is not 0, as we have shown here, right? So in order to test this entire RCC theorem to this equation to be 0, the control volume term cannot be 0 as well, because that is like they want to complement the value shown in this control surface part. So we know that for this control value term, which is this one, cannot be 0. So this option is also wrong. And this B represents the intensive property, and we know that we do have a flow, an actual flow with the density happening in this system. So this B cannot be 0. Otherwise, the control volume term will also be 0, and the control surface term will also be 0 if the B is equal to 0. So we now already know that the control volume control surface term cannot be 0 according to the information given by this problem. So this B must not be 0. So at the end, according to the condition that we have in this problem, we know that only the option B is correct. Okay, so let's move on to the next one. In the problem 5.48, we have a diagram shown here. Both pistons are moving to the left, but piston A has a speed twice as great as that of the piston B. Is the water level in the tank A rising, B not moving up or down, or falling? So we will apply a similar concept using the continuity equation to analyze this problem, but I don't want you to remember multiple equations, so that's derived from the Reynolds transportation theorem. So you should remember this equation. I mean, in your textbook you probably write like this. Yeah, but I just want to differentiate the total derivation and this local derivation. So I will use this larger D in my writing. Okay, so let's just write this form. And as we say before, that we have the control volume term. This is the control volume term. And we have the property B, though dV, the volume, plus the control surface term. We have the property B, though V times dA. So how do I get this Reynolds RTT equation? You can, I will just refer you to the textbook. Oh, you can ask me in the recitation, and I can explain it if you cannot understand what the textbook is talking about. But let's just assume we know this RTT equation shown here, and if this B property is equal to 1, then this entire RTT equation becomes a continuity equation that we will use to solve this problem. So when B is equal to 1, this is become dN divided by dt, that is the m is the mass, is equal to, and this is 0, partial t to this control volume part. B is 1, so we have dV, the volume, plus this is 1 now, so this is V dA, and that is equal to 0. Okay, so this is the continuity equation. Okay, so now you don't need to remember two different equations, just need to remember this RTT equation, and you can easily derive two other balance equation that we will use throughout this chapter. Okay, so after we know this relationship, we know that the control volume plus the control surface term will equal to 0, and so we will apply it. We say that our control volume in this problem is this middle part. Okay. So when the piston moving left, this become the outflow, and this is the inflow to this control surface, which is also have the boundary of this dotted line. Okay, so we know how the system looks like, and we will apply this equation. So I will just write these as a CV term, and that's fine. I just don't want to use other notation, so let's just write it down. That 0 will equal to this CV term. Okay, plus the outflow and out the mass that flow out of this control surface minus N in. Okay, so we have this equation, and we know that the flow can be further written into the form of these. So let's say the piston A have the speed twice as great as that the piston B, so we have the volume VB at this piston B, and VA is equal to 2 VB. Okay, so for the outflow, this is equal to Rho times 2 VB times the area at this piston A. This is Rho VB A B. Okay, and this part, the we can take this because we assume that this is not compressible. The liquid is not compressible, so the density is a constant. So we can, the first step, we can take this Rho out of this partial derivation. So this become, and I will just write this into just one integral instead. But I denote it as CV dV. And this volume is equal to the area of this control volume times the height of this control volume. The height is h. Okay, let's say that is h. And the area of this control volume, this is A. So the entire volume is A times h. Okay, so we can further write it to A times h. A times h. Okay, so that's this part is equal to this. Okay, and we know that only the height will change in this control volume. The area will be the constant, so we can again move this area out of this derivation. So the rest of the part will just be the changing rate of the height. Okay, and that is exactly what the variable that we want to solve. So now we have rewritten all those terms in this continuity equations. We can reorganize this equation a bit. So 0 will equal to A T plus Rho 2 BB AA plus Rho BB AB. Okay, and I cancel. And I cancel this low term because they are the same. And I will isolate this variable that we want to solve. That's fine. So partial h partial t is equal to a 1 over a VB AB minus 2 VB A. Okay, so the V is the same, so I take it out. A VB AB minus 2 AA. So that's C. The the diameter for the piston A is 3-inch. Diameter of the piston B is 6-inch. So the A rear for the piston B is equal to 4 pi B is 6 square. A is equal to 4 pi 3 square. So we know that this is 4.36. 4 pi is 9. Okay. So from here, this relationship here, we know that AA is equal to a quarter of AB, right? Because 9 times 4 is equal to 36. So we apply this relationship to this equation and we further write it down, and this becomes VB divided by A. This is A 1/4. Okay. No. This is AB minus 2 AB 1/4 AB, because we know AA is equal to this. Okay, so we denote this, and this become times 1/2 AB. So this become VB AB divided by A. And this is the partial H, partial T. So we have this final equation. So what this tells us, we know that the velocity of B is a positive number, and this area is also a positive number, and this area of the control volume part is also a positive number. So this entire term is a positive term. So that tells us this rate of the rising rate is positive. So we note that the water inside this control volume is rising, because we know that this change of this H rate is increasing. So the water is rising. So basically, in this problem, we start from the general RTT equation, and we apply the property B equal to 1, and then we will get the continuity equation, and based on this continuity equation, we define the control volume in this figure, and apply that to the continuity equation and simplify all those terms, and eventually we will get this variable that we try to solve. And after you identify and simplify and all those terms, we will get that the partial H partial T is a positive number, and that tells us the water inside this control volume is rising. Okay. Okay, so now let's look at the problem 5.49. To string discharge into a pipe as shown, the flows are incompressible. The volume flow rate of the string A into the pipe is given by QA equal to 0.1 T cubic meter per second, and that of the string B by QB equal to 0.006 T squared cubic meter per second, where T is in second. The excess area of the pipe is 0.01 meter squared. Find the velocity and acceleration of the fluid at the axis at t equal to 1 second. So we want to solve first things is the velocity. Okay, let's start with the velocity first. And we will apply the continuity equations. And according to the previous question, the continuous equation is looked like this. I will just rewrite it. This will equal to 0, and this equal to the control volume term plus the control surface term. Okay, and because the flow is incompressible, so this partial though partial t will be, this unsteady term will be equal to 0. Okay, so this basically gives us the simplified continuity equations that only consider the control surface. And for the control surface, we know that it means the inflow to this control surface is equal to the outflow. And so that's first defined here as our control value and the control surface as well. So we have 2 inflow and 1 outflow. Okay, so let's write that out. Q exit will equal to QA plus QB. Okay, so this is the result of this concept that the inflow equal to outflow. Okay, so Q axis, and we know that Q equal to A area times the velocity. So if we apply that to here, we can write this equation to the velocity at the axis is equal to the area of the axis over 1 QA plus QB. Okay, so I basically use these to split the area and velocity. And we already know that QA is equal to 0.01 T and QB is equal to 0.006 T squared. And the area is 0.01 cubic meter for the axis. So we can plug in all those numbers. 1 over 0.01. This is 0.01 T plus 0.006 T squared. And this gives us T plus 0.6 T squared. right? So when the velocity and we want to solve the velocity as a t equal to 1, so we plug t equal to 1 to this equation, and this gives us 1.6 meter per second. Okay, so that is for the velocity part. And now we want to solve for the acceleration. And we want to solve the acceleration along a path line. At the is equal to x exits. So basically, this is saying that we want to solve the acceleration at the middle of this tube at the exit. And to do that, the acceleration is equal to partial v, partial t, the local term, plus v, partial x, and this is the convective term. And because we want to solve the acceleration along the path line, which we define the direction of x, and according to this question, the velocity only vary with time, but not with the position. Because one of the reasons is because it's incompressible. So we can delete these parts and only look at the local acceleration. And because we already know that the velocity is equal to t plus 0.6 t squared, we can just take the partial derivative to this equation with respect to t. So we have 1 plus 0.6 times 2 times t. Okay, so this is 1.2 t plus 1. Okay, and again, we want to solve t equal to 1, so the results of acceleration at the axis as t equal to 1 is equal to 2.2 meter per square second. Okay, so just a quick review. For the velocity, we will apply the continuity equation, and because it's a compressible flow, so we can cancel the unsteady term, which is the control volume term here. And for the acceleration, we will use the total derivation for on the velocity, which is showing the equation here. And because this is incompressible and the velocity only varies with the time, not the position, according to the equation that we solve in the part 1. As you can see, the velocity only varies with the time, not the location. So basically, when you take the partial derivative to x, it will equal to 0. Okay, so we only look at the local change, which is this first term here. And then we take the partial derivative to t, then we got the equation and we solve it and plug in t equal to 1, then we got the solution. Cool. So let's move on to the next one. In this question, 5.75. How long will it take the water surface in the tank show to drop from h equal to 3 to equal to 50 centimeter? And this 50 centimeter is equal to 0.5 0.5 meter. When we define the diameter of this large tank is d equal to 0.6 meter because it's 60 centimeter, and the diameter of this outflow pipe, this part, is equal denoted as lowercase d, that is equal to 0.03 meter. Okay, so now we want to first derive the equation and then plug in all those numbers. So when you write the quiz, please also remember, try to write down the equation first before you plug in any number for calculation. Okay, so again, for this problem, we will also apply the continuity equation. And for that, we need to define our control volume. And in this case, the control volume will be the water body in this tank. Okay, so let's first write down the equation first for the continuity equation. T is equal to the control volume term, so dV plus is dou V dA. Okay, and this will equal to 0. And we can further write these things because dou times the volume is equal to the mass. So this is basically the mass change in this control volume divided by partial t, plus this is the control surface, right? So it's the inflow, it's the outflow minus the inflow that we keep using in our previous questions. So this can be summation of the flow rate. That go in and out of these outlets. So let's know that this is out. I will just write the flow rate here, okay, for generalization. That is equal to 0 over this control surface. Cool. So as we can observe from this diagram, when the water being drained out from this outlet, the control volume actually decreases. So we cannot cancel the control volume term in this case. That means we will need to derive the equation from this part for both of these two terms. We know the mass inside this control volume is equal to the low times the volume, which is the area times the height. So this partial n CV partial t is equal to partial dou I d squared divided by 4 h and partial t. And we know the pi and d are both constant. Only h will vary with the time. So we can write those constant terms out to the front. which is dou pi d squared divided by 4 partial h partial t. Okay, so we have the first term. And for the control surface term is in and out, and we don't have any inflow to this tank. So the inflow part will be 0, but we do have the outflow for this term. So this summation is rate will equal to the outflow rate, and that is dou pi d squared divided by 4 times the velocity. Times velocity, which is square root of 2gh. So again, this is a, this is v, and this gives us the flow rate, and flow rate times the density equal to the mass rate that we want to calculate. Okay, because this is the continuity equation. Okay, so let's write these two terms together and plug back to the equation that we back to the continuity equation. So what we got here is dou pi d squared divided by 4 partial h partial t is equal to dou pi d squared divided by 4 square root of 2gh. Okay, let's cancel the common parts at both sides. And we want to integrate over this partial h and partial t, so we use the method of separation of variable, which we put OH term to the left hand side and put the rest of the term to the right hand side. So we just take these, let me rewrite it, okay? D squared partial h partial t equal to 2g times h, and this is okay, that's, don't make things more complicated. And now we can move the h to this side and this d to this side. Oh, forgot one term, d squared. So we have these partial h equal to d squared divided by d squared 2g dou t. Okay, and this is the constant. So on the right hand side is relatively easy. You just d squared divided by d squared 2g t. For the right hand side, t2 minus t1. Okay, you just take an integral. For the right hand side, that's right here, okay, is h minus 1 over 2 partial h, which is dh now. And taking integration is that it will become minus 2 h, this is t2 minus h t1. Okay, because we want to integrate from t1 to t2. Okay, and did I make any mistake here? Yes, I do. I missed one minus sign here. Okay, because remember originally it's on the same side of the continuity equation, so I move this term to the right hand side. Therefore, I should add a minus sign here. Okay, and let me put a minus sign here. Now we plug the integration results to this equation. So we just cancel this minus sign. It becomes 2 HST2 1/2 minus HST1 1/2. Now we have this equation, we can start to plug in the number, and we're assuming that the T1, which is the initial of this problem, is equal to 0. So we can further write it to d squared d2 to g t2. And the question asks us to find this t, right? Because it's how long. So we actually want to find this t2. And okay, because we want to find this t2, let's first isolate it to the left hand side. So t2 is equal to 2 h as t2 minus h0, which is the initial height of the water in the tank, divided by 2g, and these will be d1 and d squared. Okay, now let's plug in the volume. This is 2 times h as t2 is 0.5 meter. Okay, so h2 is 0.5 meter, and I just found I've made a mistake in the integration. So this is actually T2 minus T1. Why? Because this, no. Let me rewrite here. So this is still T2 minus T1, but there's no minus sign in front of these two. And because originally our continuity equation have this minus sign, so we have minus sign here. So when we plug this integration back to this equation, we put this minus sign into this h, so these two parts actually switch. So this 1 minus 2, okay? So this is 0 minus t2, okay? So now we can plug in the number, which is h0 is 3 meters, so it's square root of 3 minus square root of 0.5 divided by 2 times 9.81, because the g is equal to 9.81 meter per second square. and times d, which is the diameter of the tank, that is 0.6 squared, divided by the diameter of the outlet pipe, that is 0.03 squared. So now we can conclude that T is equal to 185 seconds. Okay, so let's quickly overview this 5.75. You start from the continuity equation and you can write into the main flow terms, which you have this unstated term for the control volume part, and you have this summation term for the control surface part. And because the control volume in this problem will vary with the time, so you need to calculate this mass in terms of the variable of h, which is this equation shown here. And for the control surface term, is the inflow and outflow as balance between, right? So it's the outflow mass rate minus the inflow mass. And we don't have any inflow to this control surface boundary, so we only consider the outflow term. Then you can write down, you can plug these two terms back into the continuity equation, and you got this one. And you do some simplifications and use the separation of the variable strategy to do the integration. But just careful that when you do the integration, you need to use the right sign. So after you plug this integration back to this original continuity equation, you will get our final equation when you isolate the time to out from the continuity equations, which show here. And then you just plug in a number and you can calculate the answer for this problem. So make sure that you know how to derive a loss equation, because that is the main focus when writing the homework. It's not about the number, but about how you derive all those equations step by step. Okay, now let's look at the next one. The problem 6.7. The balloon rocket is held in place by the force F. The pressure inside the balloon is 12 inches of water. The nozzle diameter is 0.4 centimeter and the air density is 1.2 kilogram per cubic meter. Find the excess velocity V and the force F, neglect friction, and assume the airflow is in viscid and rotational. Okay. Now we know the property dou is equal to 1.2 kilogram per. This is given by the problem, right? And our strategy will be trying to find the velocity at this nozzle using the Bernoulli equation, and then to find the force, we will apply the momentum equation. So let's take step one. Step one, we want to find the velocity at the outlet of the nozzle using Bernoulli equation. And we know that P is equal to 12 inch of H2O, and this is equal to 2989 par. Though, and the Bernoulli equation tells us P divided by though is equal to 2 over v squared, we don't have the elevation term because they are on the same datum, so that term just be cancelled out. Right. So I didn't write the Bernoulli equation from the beginning, but you should know that this will be the point 1 and this will be the point 2 as you defined in the previous homework. And then you assumed you know the pressure in here, and there's no velocity at point 1, and the data is the same, so we just ignore the elevation term. So for point 1, we just have the pressure term, and for point 2, we don't have the pressure because it's open to the atmosphere, and we don't have the elevation term, and that means we only remain the velocity term. That's why we have this simplified Bernoulli equation here. This is for point 1 actually, and this is for point 2. You should know how to get from your original Bernoulli equation to this step, because if I take this question for the quiz, I will ask you to show me the simplification step. But here we just use this final solution for this Bernoulli equation. So after you know that, you can simply plug in all those values. That's first isolate the velocity turned out, and this will equal to 2p divided by dou, and that is 2 times 2989 pa divided by 1.2 kilogram per cubic meter. And then you use calculator, you will get the value 70.6 meter per square. Okay, this is for the step 1. And for step 2, we want to solve the force F. And the idea is that this fluid be ejected out from this nozzle will provide a momentum, and that momentum is equal to the force that we want to solve. So according to the momentum equation, that's the summation of the force at the x direction will equal to the summation of the outflow mass rate times the velocity minus summation of, this is the for control surface term, mass of the inflow times the velocity of the inflow at the x direction. Okay, so in this question we don't have the control value term, okay? And we only have outflow mass flow rate here, so this term for the inflow part is equal to 0. So that being said, this F will equal to mv is equal to dou a v squared. This is the velocity, and we can plug in a number. That the dou is 1.2 kg m squared cubic meter times the velocity is 4 pi over 4 times the diameter 0.4 centimeter, that is 0.004 meter, 0.004 meter square times 70.6 velocity which we got from here, and then we can have the number is equal to 0.0751 Newton. Okay, so for solving the velocity and the force, for the velocity you apply the Bernoulli equation and you define the point 1 and point 2. After that, you will apply the momentum equation to solve the force. Okay, now let's move on to our last question for this homework. Problem 6.13. A horizontal water jet at 70 Fahrenheit issues from a circular orifice in a large tank. The jet strikes a vertical plate that is normal to the axis of the jet. A force of 16 pounds is needed to hold the plate. Okay, let's write this condition down first. Against the action of the jet, okay, if the pressure in the tank is 25 psig at point A, what is the diameter of the jet just downstream of the orifice? So we want to solve this diameter here. Which is denoted as this lowercase d. So when after you look at this diagram a little bit longer, you will find, okay, they actually have a similar concept of the three previous questions. It's so similar, right? So the idea will be the same. You try to use the Bernoulli equation to solve the velocity at this outlet, at this nozzle, and then you apply the momentum equation to build the relationship between that water jet and the force given by the problem. So we'll follow the same logic. And even the simplified Bernoulli equation is the same as the previous question, if you denote this A as the point 1 and this outlet as point 2. So I will skip that simplification step, but you should know how to do it. So let's solve this V first. That's PA divided by rho is equal to V divided by 2, V squared divided by 2. Okay, and that is that V is equal to 2PA divided by rho. And rho for the water at 70 Fahrenheit according to the table at the appendix 8.5. This rho is equal to 1.94 slug per cubic feet. In plugging number, that's 2 times 25 psig, and you do the unit conversion. 144 inch square divided by feet square divided by 1.94 slug per cubic feet, and take the square root. This will give you 60.92 feet per second. Okay, now we have the V. We want to further apply the momentum equation to build up the relationship of this force and this one object. This is minus V1x. Okay. And okay, in this case, this will be minus m dot v1. Okay, so this sign will just be cancelled out. That's v m dot times v1, and this is equal to rho times av1 squared. So the area is equal to the force divided by rho v1 squared. This is equal to 600 pound divided by 1.94 slug cubic feet times 60.92 feet per second square. This will give you A equal to 0.0833 feet square. Now, we know that, and we assume a circular intersection area for this object. So this A is equal to 4 pi d squared. This is equal to 0.0833. So d will equal to 0.0833 times 4 divided by pi. Take the square root, and you can solve that d will equal to 0.326 feet. Okay, so basically follow the same logic, apply the Bernoulli equation to solve the v, and then apply the momentum equation to solve for the x. Then you can get the diameter you need for this water jet in order to hold this plate in balance. Okay, so this is then the end of this recitation, and see you in class.